So in today's session, we have the opportunity to look at decision-making with variability. This will be one of the most useful techniques because it helps us both understand our data and also interpret a number of findings that you often find in popular media to interpret whether or not a trend is important. And so today's topics, we're going to be looking at identifying the different types of ways of displaying the data so that we can actually compare variables to each other. We're going to be looking at the use of scatter plots to help with this visualization of variation. We'll be defining z-scores and the empirical rule. And we'll also be utilizing box plots that will help us detect some outliers, a very useful technique in SPSS. I love this quote by Salvador Dali, the famous painter. "I'm not strange, I'm just not normal." And this is very appropriate for the topic today as we're looking at how normally distributed data are across a spectrum of measures. When we think about our data, the last session, we looked at the different ways that data could be thought of as either categorical or quantitative. Some of the examples that we reviewed there that were categorical were, for example, in a store, the items could be located in different sections, such as produce or dairy. Those would be different categorical kinds of data. We can also look at quantitative data. In those examples, we were looking at some interval and ratio scales. The interval scale would be an example of what aisle in the store something was chosen from, aisle 1 versus aisle 4. And we looked at ratio data that would also be quantitative. That would be, for example, the price of the items. So you can see here there are some similarities in the ways that these data are represented in graphical ways. So they share our ability to look at them in terms of frequency distributions or cross tabulations. But there's also some unique things that we get to do with quantitative data that look at the dispersion and the range of values. And those are areas that we'll be getting into around histograms, box plots, and especially scatter plots, one of the more useful ways of actually looking at the dispersion of data. So typically, when we are utilizing one of those visualizations, you can be pretty confident we're probably looking at some kind of quantitative data to begin with, which is a clue of the kinds of data that you have to work with. It also will save you a lot of frustration if you're trying to look at some kind of data that's categorical and you're not able to get SPSS or some package to give you a visualization like a scatter plot. It may be that it's just an inappropriate way of visualizing the data. So this is a very useful tip. So when we're looking at the summary of two different variables, this is one way that we can begin to see the relationship. So for example, a manager might be interested in some kind of graphical measure or relationship between two variables, and we can use cross tabulation for that. It's kind of a minimalized way of looking at visualization, and that it's not very graphical compared to something like a bar chart or histogram, but it's very useful. And it's very flexible. The cross-tabulation approach of representing the data can be used in all kinds of different combinations of variables, both categorical and quantitative. You can see these, and I'll illustrate this in just a moment with some examples. So let's start. You might recall that we were looking at IQ scores across different schools, or at least we are here in this example. And what we can see here, we have two categorical variables here, the first being male and female, and the school that the students are in, A, B, C, and D. You see, you know that you're dealing with categorical data because you can't take an average of any one of these. What's the average of school A, B, C, and D? Well, you can't do that. So we know we're dealing with some kind of categorical variable, but we can't count the frequencies and represent them in a cross tabulation. So this is very useful and a very common way of first looking at our data. We can immediately see, looking across the rows here, looking just at males, for example, we can see that there are no males in school A, B, C, and D. In fact, they're all here clustered in school D, 60 of them, representing almost 47% of all of the sample that we had. And we can see this in a total here in the very total column. And then we can also see where the females are distributed across all the schools similarly here, looking across the rows. So we can see here in total there's 53% females in the sample, and looking across the rows now we know what percentage of them were attending each of the individual schools. Looking at the data this way and in the cross tabulation, I can also see here that we're looking at row totals, and that's how I was able to evaluate the percentages, adding up all the way to the percentage of females in this total column, all the way for the total of males in this column, and then down that we get 100%. So this data is representing row percentages. This is important because I'm going to illustrate this in a moment. One of the other ways that crosstabs can be used is by looking at column summary of data, and it'll be very obvious in the illustration in just a moment what the difference is. So I find it useful to just look at one or the other, at least to look at the patterns before I look at both, which can often be an awful lot of data for any manager to take in. Let's look at a second example. Now, these are two categorical variables, but I said that it's very flexible. This technique can also look at a combination of different variable types. So here's an example where we have both categorical and quantitative data. The categorical data are the school. So again, we have here represented school A, B, C, and D. So we just have a number of students that are in there. But now what we're representing is their IQ scores that are present in those different schools. And so this is going to be our quantitative data that's running across this way. So the way I'm interpreting this here is I know from this that I have the IQ score of 121 IQ points occurring really, I can see here, just twice in school D, which represents here 22% of the total number of IQ scores that I have in this sample. And again, I have the clue here that I'm looking at row totals, because as I go across the rows, I get a total of all of the observations that I saw in that school for those IQ scores, and I can add those up and it gives me 100% total. So this is a very helpful way of looking at a combination of categorical and quantitative scores to give me an understanding of how they're dispersed or their relationship to each other across both types of variables. I'll illustrate another example here where we have two quantitative variables. And here we've just taken a truncated set of these for illustration purposes. Some of these tables can get quite large when you're looking at a lot of quantitative data because there could be a lot of elements in between. But here we just have a snapshot, again, of the very top IQ scores, that is those above 121 to 133 in my columns. And then across these rows here, we have anxiety scores. And all of these are being added up. Again, I can see here that, for example, here I know that this one observation of an IQ score of 131 and an anxiety score of 91 occurred only once. That one observation represents 12.5% of my sample. And across all of the anxiety scores of 91, I can see it only occurred twice, which represents 25% of my sample. If I were to add that all up, I can see I have 8 observations in total, representing 100% of my sample. Those are the 8 IQ scores or sample students that I have, and it shows me all of their data, both in terms of IQ score and anxiety. So it's very helpful to represent that. But you can see it's getting to be quite unwieldy, which is why this technique is useful but difficult as the data set gets rather large. Now, I wanted to also illustrate how we have been looking at the row percentages here for the anxiety score and the test scores of IQ, but we can also look at the column percentages. And I know that I'm looking at column percentages in the crosstabs because immediately you can see the difference if you compare the two. Now I'm getting 100% total in my rows. This is a different interpretation here. So now I can sort of look at within an IQ score of 121, what level of anxiety did each of those IQ scores represent and give me a total. So I can see that 50% of those who had an IQ score of 121 had an anxiety level of 87. And again, here, within those who had an IQ score of 121, one of them had an anxiety level of 103. So it's a different way of representing the data. When you ask SPSS for this, it can give you both of these all at once, and it can be useful, but you can imagine that it's a lot of data to take in. So my coaching to you is to make sure that you know what you've requested and make sure you're interpreting it the right way. And it might be helpful to look at one at a time before you can fully interpret the patterns of the data looking at it just in crosstabs. And we'll look at some of that in some later sessions. Now we're going to turn our attention to how we can look at variation in the data. And I want to look at just one variable at a time before we can expand this to more complex situations. So these tabular summaries, like in a table, they have limitations because it can be difficult to see the relationships. Just look at the example I just shared with you. Is it very easy to interpret the relationship between anxiety and IQ score looking at the example just prior? It can be very difficult for us to pick up those patterns. So we need to look at some graphical display of that information to help us better interpret that. So let's look at this variation first. Here I have the same IQ scores of this small sample. There's actually 8 total IQ scores in this sample that I have across the schools. I know that in a number of ways. I can look over here on my descriptive statistics. It's telling me that there's 8. Of course, it's such a small data set, I could just add it up. I've got one person with an IQ score of 79 and one person with an IQ score of 33. We've also see their student ID numbers here, and these are just dummy variables that we've assigned to the observations or their student ID numbers that's independent from their IQ score. So it's not something that has any information value other than just keeping track. Those could be people's names. This could be Sally, and this could be Tom. We don't know that. They're just observation student numbers there to keep it straight. But all this data that we have in our descriptive statistics over here, that's telling us information about our IQ scores. So I know here that the average IQ score of the 8 total in my sample was 110.5, so it's a little bit better than average. The median value was 111. IQ scores typically, above 100 means, being average, so I know that this sample is above average. Then we have some other interesting things that we're going to talk a little bit more about today with variation, the standard deviation and the variance. So what are these values and what is the table telling us? Those are good questions. We want to look at that. We're also going to be looking at values related to the range of the IQ scores and the minimum and maximum values. That is, how big of a range do I see between an IQ score of 79 and 133? And what's the dispersion of these scores? That's what we're trying to understand better. And then finally, we see the percentile. So I know from the calculation here that 25% of all the scores fall at or below the 99.25 level of IQ. And I know that 75% of all the observations fall at an IQ level of 123.75 or higher. So these are, again, measures of dispersion. So the computer's telling us that. Let's try to understand a little bit how we got there. Here I've represented those same 8 student IQ scores from school D. These are all happen to be female students at this school. And we have their student ID numbers across this x-axis. We can see each of them represented here. So this is literally student 8's IQ score of 110. So if you rewind the video or if you have the slides, you can check and you can see, oh yes, student 8's ID score was associated with an IQ score of 110. So we have them all plotted here, all of the IQ scores on this axis. And we can see that there's some range of values here. And I want to actually represent that. I can see the range now because I've plotted it between the lowest score of 79 and the highest score of 133, which you could just subtract, of course, 79 from 133 to give you the range. The range is 54 points, so 54 IQ points. or the range that's represented here in the data, but it's also helpful to see it visually. So the dispersion is telling me and giving me a picture of how much variation there is. How different are the different students in my sample in terms of their IQ score? So range is one of the most simple ways of us giving ourselves that picture of that dispersion. But we can go further. This is really, to get a little bit better of an understanding of that, we need to look at the mean or the average IQ score. So if I added up all the IQ scores and divided them by, here it's 8, it's going to give me that mean of 110.5 in terms of average IQ points in the sample. Now, this is really useful to me, and we get to do more sophisticated things to help us understand the dispersion or the range. The first thing that I can do is maybe look at the deviation. That is, how far away did each observation fall from the mean? And I could take that, so I'll just flip back. 79 was the value represented by this point. And if I take 79 from the mean of 110, I can see that I'm 31.5 IQ points away from the mean. That's this distance right here. And if I do that for each of my scores, I actually start to get a picture of how much deviation there is from the mean. If the score was practically on top of the mean, as it was here, I don't have very much of a deviation at all. So I have a score of 1.5 because I'm simply taking the score that I observed from the mean, and I can see that there's practically no difference. The smallest one is actually right down here. And so student 8's observation was 110. That was their actual IQ. So when I take the difference, I'm only got a difference of a half of an IQ point, very, very small deviation. So that's one way for us to understand that. But the mean deviation is typically used as just a starting point to look at a little bit more of a sophisticated statistic. What we want to do is really maximize the variation that we can talk about in the sample so that we can understand it better, because some of those differences are really tiny and other differences are really big. So by taking the square of the mean deviation, it starts to help us maximize the scores that are far away from the mean and minimize the ones that are closest to the mean. And you can see that here. These are the same values that I had represented in the prior slide. I've just squared those values. So you can see that those scores that were far away, now the number is quite large. That's what the deviation is doing for us. Scores that were relatively close to the mean, the difference is even sort of minimized. Remember, this was the score on my mean deviation that was just 0.5, a half of a IQ point difference. Now I'm at a quarter of an IQ point difference by taking the square. So going deeper, now that we have the squared mean deviation, we can do something very, very useful, which is actually calculate the variance. So the variance is that mean squared deviation that we just calculated, and it is basically a way of interpreting the difference in terms of squared units, which is a little bit hard to maybe conceptualize for some data. So I know that this student's IQ score is 992.25 squared units of IQ away from the mean. So you can see it's a little bit awkward. Here's the formula here if you actually wanted to do this by hand or in Excel. Typically, we would just have the computer be giving us these statistics. So it's more important that we just conceptually understand what's going on. That the variance is the sum of those squared mean deviations divided by n minus 1, because we're dealing with a sample here. That's going to give us the variance. So the variance on average, when I take all of it, when I account for all of these values, and I divide them by the total in the sample, this is what's giving us the variance. And if you look back, that's what SPSS was telling us, is that we had 287.71 squared units of IQ variation in our sample. Now, to make this a little bit more interpretable, we do something very simple that's very effective to help us interpret this, which is starting with the variances. We can compare two samples like this. So here I have an illustration of school D, which is all of the data that we saw already plotted in the circle dots. And I've also represented another school by comparison, which is school A for the females. And we can see which school has more variance. Well, which of them do you perceive to be closer to the mean? Both of these schools, according to this data, happen to have the same mean of 110 IQ, but you can see that students from school A have less variance. That is, their squared units of IQ around the mean are tighter. So there's less variance in that sample. And here's the measure here. We've actually calculated that using this formula. So you can see that in terms of squared units, going from 287 to 65 in school A, there's less variation. But again, I'm still having even a hard time talking about it in terms of square units of IQ. So what we can do is take the square root of that, and we can actually now interpret it back in terms of the original measure of IQ points. And this is much more useful. It's way more intuitive to talk about variance this way. So when I do that and I take the square root of that, I can see that my standard deviation for school D, my original school, is 16.96 units, or IQ points. And that's a little bit more intuitive. I can do the same thing for school A by taking the square root. Now I'm down to 8.11 IQ points. And now it's very easy to say, well, sure, students in school D, the average deviation, that is the average number of points that the students differ from each other, in school D is 16.96 points of IQ. And for school A, we can see it's 8.11 points of IQ. So again, very similar interpretations. We can clearly see that there's less variation in school A, but the squared variance, which gives us the standard deviation, square root of the variance giving us the standard deviation, is much more interpretable back to the original measure. So we tend to use that a bit more. Here I have represented that data for all the schools. So if we were to continue to do that with IQ points for all of the schools, and I got their means, I can calculate their standard deviations. There's one more metric that's often referred to that's very useful, which is the coefficient of variation. So that's just basically taking the standard deviation, divide by the mean. So you take this number, divide it by its mean, and then turn it into a percentage. I have the formula right here if you wanted to calculate that. But now we can interpret it in terms of average dispersion or average variability in the sample. This is often used in business because you would like to know how much coefficient of variation a sample has, because it tells you something about effectively how much change you could expect or how much risk there might be. So here we're just using the illustration of IQ points, so I can see that and interpret that, the average IQ in school A is only varying about 7%, and the average IQ in school D is varying, 15%. But what if this happened to be maybe accidents that are happening on your shop floor in your warehouse? It would be useful to know that the number of accidents in, say, aisle A versus the number of accidents in aisle D have such a wide range of variation. And then you can put more effort to try to minimize the risks that are happening in aisle D. Maybe aisle D happens to have maybe more heavy items to move, and that's why people are getting more injured moving those items versus items that are lightweight. And so it's a way of helping you interpret risk, and that way you can take appropriate action. So, of course, we have formulas. If you have any kind of text or reference, you'll find formulas that look something like these. So if you would like to try to map that back, you, of course, can see how that operates. But in an applied class, I'm less interested in how those things are being visualized and more interested in how you can actually use the tools to get the statistics and then interpret them. So let's continue on with that idea as we're starting to look at z-scores. Z-scores are another way for us to work with the standard deviations in our sample to help us understand variability. This is one of the most useful statistics that you'll see. You can use it pretty much every day looking at data that's often reported in common news outlets to try to understand differences between samples. So once again, I'll start with the IQs that we have for our 8 students. So we have our IQ scores here, and we know we had calculated earlier that the mean was 110.5 IQ units, or an average score of 110.5. Now what I'm doing here is I'm basically just taking the mean of that sample away to get my deviation from that mean. And now I can divide that by the standard deviation to give me my actual z-score. So this is the formula here that we just did. Every score minus its mean divided by its standard deviation is going to give you the z-score. Now, this is very interesting. It has some unique properties. You might notice that when the IQ score, such as 79, was below the mean value of 110, it produced a negative z-score. This is literally telling me that the z-score, that the IQ score of 79 is minus 1.86 standard deviations from the mean. That's very useful information, and it really shows you how the visual layout of the same scores that we looked at just a few slides ago can be interpreted in terms of a number. You can also see the patterns that when the IQ score was above the mean, like 120, as we see here, it produces a positive z-score. So an IQ score of 120 is about a half a standard deviation, 0.56, above the mean. And you can see the pattern here. By looking at all of this in natural occurring data, things like height, weight, IQ scores, or other kinds of natural phenomena like weather, we can see over time that there's a pattern to all of these observations that is rather empirical. In fact, by looking at these things, we can go further and look at how these things are distributed across a wide range of phenomena, looking at z-scores. So again, just to summarize, what we're talking about here is the relative location of a score or an observation from its mean. A z-score will help us interpret that in the data set very quickly. I've already shown you how a z-score that is above or below the mean is going to have a positive or a negative value. If a z-score happens to be exactly equal to the mean, it's going to have a score of 0. And so we're able to now interpret this in a chart or a graph. So these are really all the phenomena around z-scores that I just summarized verbally a moment ago. But where I was going with this is that we can use this to help us interpret naturally occurring phenomena. We refer to this as the empirical rule. When the data is believed to be practically normally distributed, which would be a bell-shaped curve, and it would be called a standard distribution, the empirical rule can be used to help us understand where the data is likely to fall. We know by looking at observations naturally over time that about 68% of all the values that we're likely to observe will fall between plus or minus 1 standard deviation of the average, of the mean of that sample or of the population. And approximately 95% of all the data between 2 standard deviations of the mean. And I'll show you what this looks like. It's probably going to feel familiar. Almost all the data that we could possibly naturally observe are going to be within 3 standard deviations of that mean. So this should probably look familiar, and this is just maybe a refresher to some of you that this is exactly what we're talking about, that the average of some observation being in the middle, a bell-shaped curve, is telling us that within 1 standard deviation plus or minus from that mean, we're going to see 68% of all those scores. We're going to see 95% of all the values within 2, and almost all of the data should typically fall within 3 standard deviations above or below that mean. So let's take a look at that. Remember the z-scores that we had before. How normally distributed are those scores? Well, we can sort of plot them here around the average that we had calculated, which was 110 average IQ points was the mean of that sample. And we can see more or less, we actually did observe scores that were sort of falling in that range, which is what we would expect. If things are normally distributed, all things being equal, if the students were randomly assigned or observed in those schools, you would sort of expect IQ scores to fall in these ranges. Most of them plus or minus 1 standard deviation. There are some scores, very few, that fall a little bit above or a little bit below that range. So this is very helpful. So we can use the empirical rule to look at our data in general, and it will help us detect what's known as outliers. Outliers are going to be unusual scores. They can often tell us something very important that we need to pay attention to, or it might tell us something in the data that is an error that we need to actually remove before we observe or do other kinds of operations with that data. So as I've summarized here, it may be that when you observe a score that's really outside that range, it could be a incorrectly recorded value. It could be, though, a value that was incorrectly included, or it could be a correctly recorded variable that belongs in the data set, but we need to pay special attention to it. It might be telling us something really important. You'll often see these in business around areas of risk or unique segments of customers, and I'll illustrate this in a little bit. So an outlier doesn't necessarily always mean that it's bad. An outlier just means that it's unique in some way, and it deserves special attention. What I've done here is I've plotted the same IQ data in terms of a distribution of the IQ scores. And so here we have the frequency, that is the number of times that we've observed that IQ score in our data set. And we can see, around, say, the higher end, we actually do have quite a few observations. That is about 2 students here, 2 students here, and 1 student here that are on the upper range. And we know that it's on the upper range because it's overlaying, SPSS here is overlaying a normal curve on top of our data to try to tell us whether or not there are some things that are sort of outside of the empirical rule. So this could be useful for us. I might want to take a look at this. It does seem to me that we have a sample here with a relatively high distribution of IQ scores that might be unusual. I need to know a little bit more about the students that are coming from this school. We also can see here that there's some observations that are on the relatively low side. So that's also some indication here that I may want to pay attention to that. And seeing this graphically, this is a very simple example with very few data points. As you're doing this with your own data and data points get larger, these can be very useful ways for you to understand the patterns in the data. Another very useful technique that SPSS can produce for us is known as a box plot. This is another graphical way of looking at our data to decide whether or not something unusual is happening that we may want to pay some attention to. Now, the box plot has a number of different elements to it. These are known as whiskers. You can see the box that's right in the middle here. Now, some of these values are going to be probably very easy to understand and intuitive. In the middle of the box plot, SPSS will actually be putting the median value, which we know the median value from the table statistics that we can see on the left is at 111 IQ points. It's also going to be showing us where the middle of all that data is by using the percentiles. So the 25th percentile is the point at which all of the data at that point is 25% of the data is going to be falling at that point or below. And the 75th percentile, so you have 75% of the scores are captured below that point, and there's only going to be 25% above that. So we refer to these as quartiles. The data can be divided up, and the middle part of that data is represented in the box plot. Now, the whiskers are on these sort of points that we can think of them as quartile limits. And I've given you the actual formula here. SPSS, or almost any package that's producing a box plot, is actually going to be calculating the quartile limit, minimum and maximum. That's basically taking the score that is at the 75th percentile, and it's going to subtract the number or the range that's in that center point. 1.5 times that. Anything that's outside of that is going to be falling actually outside of these limits, these either limits of maximums or minimums. Let me illustrate this with some actual values from our data so that if you want to do this by hand to sort of understand what's going on, you can do that. What we can see here, as I showed you in the last slide, that the median is 111. We have the score at the 25th and 75th percentile. Well, that's exactly what we can see here. You can see it's represented here on the box plot for those percentiles. And now we can see that there's a range of 24 0.5 points. And what the whiskers are doing for us is that value of, say, the minimum, which is the 25th percentile, which is going to be subtracting 1.5 times this range, will give us this value here. And then adding that same amount on the upper end will create this very top value of 160. This is probably more detailed than you need to understand most box plots. What's going to be important to understand is what I'm going to illustrate is by seeing the data this way. It's very similar to looking at it as a distribution of another graphical way of understanding the data. And what we want to pay attention to are there any points that extend beyond that range? Because if it is, that's a clue to us that something unusual is happening, and we probably need to understand the data a little bit more, especially before we do more sophisticated operations on it. So I want to illustrate that point of it because this much is probably going to be output from the computer. It's unlikely that you're going to be doing this by hand. So let's go back where we look at all of the data in our data set, all of the IQ scores that we have. We can already immediately see, based on the empirical rule, something unusual is happening here because I can see that when the computer is overlaying on this histogram of all the IQ scores, so here I have the IQ score average of 100, I can see I have about 20 observations in my data set. And 30 observations on my data set that are roughly, close to this mean value. But we have something unusual that's happening here and maybe even right here. Stuff is starting to fall outside of the expected range. So graphically, that's one way that we can notice that something unusual is happening. But the box plot is going to give us a very similar kind of view. The box plot of this same data by each school looks like this. Most of the time I can see the schools that have, for example, school C versus school A. I can see that school A has a greater range or variability of the data of IQ scores. So it's telling me here that school C must have students that have similar IQs, more so than school A. But there's something else really special going on here, and that happens to be with school D. School D is showing me here that most of the data are falling in this range, but I have at least two values here. Do you see the observation number 107 and the observation number 101 are very unusual. And I know from the prior slide, as we looked at that, we had a clue looking at how the values here, based on the empirical expectation, was dragging off there to the lower end of the spectrum. And that's exactly what the box plot is showing us. But better than just looking at the histogram, I know the exact observation. SPSS is helping me narrow down the exact student that I need to look at. It's student number 107 and student number 101 that I need to really look at with a little bit more detail. Here again, I ran the same data of the IQ scores, but this time, instead of looking at it by students, I asked for the data by sex. And now I can actually see that the two students that really need special attention happen to both be male. Didn't have to come out this way. It could have been that observation 101 was a female student, and the data would have represented itself that way to us. But it so happens in this case, they both happen to be male students, and they're falling on the outside lower end of the spectrum in terms of IQ scores. This is really important information. So taking all this in, I had shared that the Z-scores are a very useful technique for us to look at general patterns in data. And this is a very common example that you might come across an infographic that has information like this. This happens to be a recent infographic on data scientists and their typical salaries, starting salaries in US dollars. And what it's telling me here is that the median salary for data scientists in 2016 was $116,840. And so knowing this information, I can start to interpret this with a little bit of estimation and actually start to understand the general data in a deeper way using Z-scores. So if it's normally distributed, and I don't expect any reason why it wouldn't be normally distributed, I can treat the median and the mean to be the same. the empirical rule tells us that when all the data are lined up, the median and the mean would be the same at the same number. So even though the report is saying median, we can treat that as an average score for data scientists to actually earn that. And then let's say that maybe I had some government data on the standard deviation, $15,000. So the average change from one person's starting salary to the next, if I were to just randomly sample two, would be about $15,000. And so this is very helpful to work with. Using the empirical rule, we know that 68% then of all the starting salaries are going to be within one standard deviation of the mean. So this is very helpful. I can start with that $116,000 number. I can subtract and add $15,000 to either side of that. Now I have a range of value. And I know now that 68% of all the data scientists who are hired are earning a salary somewhere between $101,000 and $131,000. Hey, that's pretty good. Now, I also know that within two standard deviations of the mean, I can get this sort of a range by doing the same arithmetic and just adding another level above and below. So now I'm at $146,000 and $86,000 US dollars for this range. So it gives me a good sense of the starting salaries in general around this by using the empirical rule. Now, what if we have a different situation where we cannot, with great comfort, assume normally distributed data? Sometimes maybe data scientists are considered mission critical to the organization, and they're so critical that they might garner a very high wage. Or maybe some data scientists are very new out of school, and they're going to have very limited responsibilities to the company, and so maybe their ranges are going to be exceedingly low. Either way, for some reason, I just may believe that I'm going to have observations that are greater than 3 standard deviations above or below the mean. And so I can't treat it as normal. In that case, we can reflect on some data that we actually do see now, especially a lot of internet selling sites have observed these kinds of observations that I'm describing around data scientists. And we call this the long tail. This was popularized most recently in a book by Chris Anderson from 2006, and there have been others that have been writing about that. When we look at sales on internet sites of things like music and movies, while it's true that some of the most popular items that are watched or downloaded or looked at are from the top 100 most popular items, there's much more that are actually in what we call the tail. So in this case, it's an example from Netflix. When Netflix looks at its data, 37% of its sales when they were selling music or movies are from the top 100 titles, but 62% are outside of that. This is very unusual. But this is more common now with internet businesses. And this means that the empirical rule may not be as useful to us in trying to understand what the typical movie watched or maybe how frequently it's watched, because there's so many movies that are being watched in these little segments. So from a business perspective, these outliers are really important to us. I wouldn't want to just discard them or take them out of the database. I want to use them in some way to maybe make myself more profitable. It would be helpful to know if the data look like this. And so then I can make an important decision about how to treat those customers. So it's a good thing to keep in mind. But we're not lost. If we do have a situation like this and we don't expect it to be fully normally distributed with a lot of activity that are actually in the tails, we can use something called Chebyshev's theorem. And what this is saying is slightly different from the empirical rule. It's taking the reverse perspective, and it says, well, if data is assumed to be not normally distributed, what I can say is that at least 75% of the data has to fall within 2 standard deviations. And the theorem says at least 89% of the data will fall within 3 standard deviations, and 94% of the data will fall within 4 standard deviations. So I can still use this theorem to try to understand the shape of the universe of, say, all the movies that Netflix has available. So Going back to the data scientist example, here let's apply Chebyshev's theorem. Maybe we believe that data scientists' starting salaries can be wickedly unusual. Some of them are just getting an awful lot of starting salary. So you learn that in the company that you work for, they recently hired a data scientist and the starting salary was $152,000. So person is doing quite well. But you have this question: what's the minimum percentage of data scientists that are earning at least that much? Here we can apply the theorem. If I use the data that I had from the Glassdoor study, and I know 116,000 is the mean of all the salaries that data scientists are earning, and we know that the standard deviation is 15,000, we can use Chebyshev's theorem in this way to say, and find the upper and lower limits. And I have the math for you here. And what this is helping me say is that I can now, with great confidence, know that at least 83% of all the data scientists have to fall within this range here that I've calculated plus or minus of these standard deviations. So even though I had a good expectation that the data is not normally distributed, I still have a useful range to say that, well, at least 83% of all the starting data scientists are in this range of $80,000 to $152,000. And so that helps me interpret the data. And this can be very useful for other situations if you suspect that your data is non-normal. And you're still using very simple arithmetic using either standard deviations, the mean and the z-score. So here I have the two empirical and Chebyshev's theorems represented side by side. It's really just a different interpretation of the range. So by the empirical rule, this sounds probably the most familiar because it's used the most, is that plus or minus one standard deviation is going to be 68% of the sample. But Chebyshev says, well, we just say at least this percentage of the sample can be within that. And it makes it very clear. Chebyshev says, look, this data is unusual. So plus or minus one standard deviation, I'm not going to guarantee you that there's any data that's there. And you can see it hedges and says that more of the data is going to be represented out in these further ranges. And so it's useful to us when we want to think about saying, well, at least how many of the observations are in that range. And that's when we're going to be using Chebyshev's. So the takeaway. We started with cross tabulations. It's very helpful to use for representing data in a tabular format and looking at percentages either in rows or columns. We advanced that by looking at how a variable is distributed around its mean, and we can use both scatter plots and box plots to start to detect outliers. Outliers not necessarily always being bad, but important for us to pay attention to. And we can use the empirical rule and z-scores to look at the quantity of the observations that we expect to be in certain ranges, usually a standard deviation around sample's mean. And if we just don't believe that we're looking at standard data, we can always use Chebyshev's to at least tell us at least how many of the observations are at a certain point or lower, or at a certain point or higher.